Dear students, I welcome you for the lecture related to the process control. Today we are going to discuss related to the dynamics of the first order control systems. Now when you talk the dynamics, what it means basically? The dynamics is the transition, transient situations, the not steady state conditions. That is nothing but your unsteady state processes that is observed. And this processes depends on certain variables with the time. So this is the variation of certain variable with respect to time. That is what the unsteady state situation, analysis of the system in the unsteady state condition. It has not achieved a steady state value. The temperature of the outlet temperature of the heat exchanger, that is not steady, and it is continuously changing depending on the action taken by the controller to provide the amount of the steam. After certain time, it takes its own time to attain the steady state where you will get a constant temperature of say 60 degrees Celsius. That is the steady state condition. But what will be its transient state condition, how its behavior will be? That study has to be done, and it requires the understanding of the certain differential equations, representation of a model, creation of a model for the system. And this differential equation representing the dynamics of the control system is same as that of the order of the control system. Depending on this differential equation, depending on the model developed for that system, means developing a model for a system is very important, and for that one requires the basic material, energy and the momentum balance equations, and this will be helpful for developing the differential equation for the particular system. Now whether this differential equation is of the first order, then your system becomes the first order, or this differential equation, if it is the second degree, then your order of the system, that can be the second order. Then to understand the response of the control system, it is necessary to develop the certain transfer function. A transfer function that is to be developed. Why? To understand the response of a control system, how that control system will behave, that is of more concern. For a particular action taken, what will be its response? When I am increasing the accelerator speed, how much speed that is increased or noted into the speedometer? That is what the response. How much time it requires. Now when you compare these mechanical, electronics or chemical systems, these chemical systems respond very slowly इमीडिएटली बहुत कम केमिकल सिस्टम्स रिस्पॉन्ड होती है. They are having their own time constants. Will require certain time to respond, to behave, to represent what are the changes. When I am increasing the accelerator speed, that means I have changed something. So to understand the response of this control system, it is necessary to develop the transfer function of a control system. And this transfer function relates to the output process to the input process. And that is nothing but represented by the GS, that is the transfer function, and which is defined as the Laplace transform of the output deviation variable to the Laplace transform of the input deviation variable. This is the general definition of a transfer function, but it is in terms of a Laplace transform of the output deviation variable to the Laplace transform of the input deviation variable. And that is why you require the understanding of the Laplace transform in your engineering degree to understand this subject only of process control. And every branch, almost every branch of engineering, there is a process control subject. And the difference is that the systems are going to vary. In case of our chemical, it can be your reactors, distillation columns, heat exchangers, absorbers, agitators, pumps. All these are our systems. In electronic systems, there are different electronic components, diodes, triodes, then your PCs, ICs. Then in case of your mechanical, your engines, your crank and shaft mechanisms. So systems may vary, but the basic fundamentals, basic equations are same. How you are going to apply for that particular system, that is going to vary. So the understanding of this process control will help you to understand the other systems also for the other subjects or other branches of engineering. So this transfer function, that is your Laplace transform of the output deviation variable upon the Laplace transform of this input deviation variable. So developing a transfer function in terms of the output and input is the necessary thing in this process control. So we will consider first few systems. So mixing tank is one of the basic systems. It is the most simplest system. Now consider a flow rate of Q meter cubes per second, that is a liquid stream of dilute salt solution. A salt solution that is there, which is dilute at a constantly entering into the mixing process, and this is the volume V, and it is having the concentration, uniform concentration C0. The inlet concentration of the salt is Ci. Ci is the concentration of the salt in the inlet stream in kgs per meter cube, and C0 is the concentration of the salt in the outlet stream in kgs per meter cube. This is what? We have defined the system. Q is the flow rate. Now in this case, the inlet flow rate and outlet flow rates, they're constant. However, the salt concentration, that is going to vary. Either the salt is already present in the tank of a certain different concentration, or the water, only water is there into the tank. Both the situations can be there. Now Ci, that is inlet concentration, the C0, that is the outlet concentration we are considering. Now what will be the concentration in the tank throughout? This is the question. What will be the concentration in the tank when the inlet concentration is Ci, outlet concentration is the C0? What will be the concentration inside this tank? It will be same concentration as that of the outgoing fluid. What is the concentration in the tank? The same concentration fluid will go out. So the concentration in the tank, that will be also C0, and the concentration of the fluid which is moving out, that will be also C0. However, the inlet concentration, that is going to vary. Now taking the balance on this salt concentration, how much amount of the salt that is coming in, how much amount of the salt that is going out, and how much amount of the salt that is getting accumulated or disappeared. Generally, you are knowing that input minus output plus generation or consumption is equal to the accumulation. Input minus output plus generation or consumption is equal to the accumulation. That is our basis for any balance, whether it's a material balance, whether it's an energy balance, or whether it's a momentum balance. In our chemical engineering aspects, we talk in these three balances mostly. That is why we give the importance to our heat transfer, mass transfer, and chemical reaction engineering for concentration balance. So, this concentration of the salt that is more concerned in this case is the input flow rate, input rate of salt, Q into the flow rate into the concentration. Flow rate, that is having the units of meter cube per second, and the concentration, that is kgs per meter cube. So kgs per second is your flow rate, that is the Qi. This is volumetric flow rate and this is concentration. So kgs per second. Inlet, what is outlet? Salt, amount of salt which is going out. Now what is the change? Is there any generation or consumption of the salt in this process? No, there is neither generation nor consumption. But consume reaction हो ही नहीं रही है यहाँ पे. As the reaction is not there, so there is no generation and no consumption. If the reactions are taking place, then one can have the changes or the study related to the generation and consumption terms. The input minus output plus generation oblique consumption, which is equal to accumulation. This is our basic equation. input minus output plus generation or consumption is equal to the accumulation. So in this case, input of the salt that is taken into account, how much amount of the salt that is coming into the vessel, how much amount of the salt that is going out from the vessel, is there any generation or consumption of the salt? No, there is no chemical reaction that is taking place. So the question of generation and consumption, that doesn't appear. And there is a accumulation, change in the concentration of the salt in the tank, that is obvious there. That is what the accumulation term. Either it can decrease or it can increase. If the salt that is already there into the tank, then, and the inlet concentration that is less, so there is the distillation of the salt. So the fluid salt that is coming in, salt that is going out, and the salt which is getting accumulated, the change in the concentration. So this is dVCO upon dt, and that is represented as V into dCO upon dt. This is one equation. This is the unsteady state equation, where this change in the concentration that is taken into account. Continuously the concentration of the vessel, concentration of the salt in the vessel, that is continuously changing. यहाँ का salt का concentration change हो रहा है. But after a certain time, a stage will reach where the inlet concentration, that will be the same as the outlet concentration. That will be the steady state condition. The inlet concentration will be same as that of the outlet concentration. There is no change in the concentration, or there is no accumulation into the vessel. So at steady state condition, the QCIS, represented as the CIS, that is what? The steady state concentration, minus QCOS, that is the outlet concentration at the steady state, which is equals to the 0. So this is the steady state equation. This is the unsteady state equation. So we are writing the two equations, the changing equation, changing of the concentration with respect to time, change in concentration with respect to time, that is what? The unsteady state condition, and the steady state condition, steady state equation. So these two equations, developing these two equations is most concern or most primary step in any system, whether it's a chemical, mechanical, or electrical or electronic system. So what is into the system, what is going out, is there any generation or consumption, or is there any accumulation? So considering all these balances, one has to develop the unsteady state equation and the steady state equation. Now rest of the part is your numerical part. Basic understanding of this, or developing these basic differential equations from the understanding of your chemical engineering aspects, we have to analyze it. Then subtract the equation, second equation, that is the steady state condition minus this equation. So Q Ci minus CIS minus Q CO minus COS, which is equal to V into dCO upon dt. Subtracting 1 minus 2. Simple steps. You have to remember these steps. There is no change. The procedure is same every time. Only one equation that is going to study it in the details. Rest of the equations I am going at a faster rate. Now, this definition of deviation variable is important. Deviation variable is the change in concentration at steady state and the regular concentration. That is what Ci minus Cis. That is what the deviation variable is represented. Concentration minus the concentration at steady state. Whether it is the inlet concentration or whether it is the outlet concentration, and represented by the Ci bar or Ci dash, that depends on book to book. So in this Ci bar, that is going to define as the deviation variable, which is equal to Ci minus Cis, and Co bar, which is equal to Co minus Cos. Therefore, dCO, differentiating this dCO upon dt, which is equal to dCO upon dt minus dCOS upon dt, at steady state change in outlet concentration is not zero. Change in concentration, outlet concentration vary होगा क्या at steady state? No, it is constant. जितना inlet है उतना ही outlet आ रहा है. There is no variation, and that is why this term becomes zero. So CO bar is same as CO. Here, introducing these deviation variables and writing this equation. Now we have achieved this thing. QCI bar minus QCO bar, which is equal to V dCO bar upon dt, and further manipulating that Q V upon Q, that is manipulated, and this V upon Q is nothing but the time constant. What are the units for V? That is the volume, meter cube, and Q is the volumetric flow rate, that is meter cube per second. So what will be the units for V upon Q is the units for time. That is nothing but the tau or T, whatever you want to write, that is going to vary. And you have to take the Laplace transform. So CIS, Ci bar S minus Co bar S, which is equal to the V upon Q, that is tau, into dCO bar upon dt, is represented as SCO bar S. So collecting these two terms of CO bar, one plus tau S, which is equal to the Ci bar upon S, and the transfer function and the transfer function is nothing but the GS, which is equal to the Laplace transform of the output deviation variable to the Laplace transform of the input deviation variable. CO bar, that is nothing but the deviation variable. CO bar, Ci bar, they are the deviation variables and defined as CO minus COS. The concentration outlet and the outlet concentration at steady state. So this is the transfer function GS for mixing processes is given as CO bar S upon Ci bar S. This is nothing but 1 upon 1 plus tau S. This is the transfer function for this system. And this is represented as the first order transfer function. Represent the transfer function relating the outlet concentration CO to the inlet concentration Ci for this physical mixing process. It represents the dynamics of the mixing process, which is the first order differential equation, and therefore it's a first order control system equation. The differential equation that is of the first order, and that is why it is called as the first order transfer function and represented as 1 upon 1 plus tau S. This is the first example. Then now we will consider the second example in which a certain reaction that is going to take place. A continuous stir tank reactor. Consider a liquid stream enters into the CSTR, which is having the flow rate Q, that is in terms of meter cube per second, and the concentration Ci, which is in terms of the moles per meter cube in this case. In the previous case, the salt concentration we have measured in terms of the kgs per meter cube. Here we are taking the reaction that is talked in terms of the molar basis, and that is why we are taking the moles per meter cube. Then they assume the reaction that is of the first order. This is one of the assumptions. So when we take the first order reaction, then it is R, which is equal to the Kc, rate of reaction, which is equal to the Kc. So R, moles of A decomposing meter per meter cube second, that is the units for R. It's a first order reaction. Then concentration, moles per meter cube, K is the first order rate constant, and the units of 1 upon S. So again applying the input minus output plus generation or consumption, which is equal to the accumulation. Now in this case, the input concentration of the reactant or the input molar flow rate of A, output molar flow rate of the A, then the molar rate of decomposition or consumption of A at molar rate of accumulation of the A. The balance is taken for the component A minus Ra, which is equal to Kca. That is why we write in terms of the Ra. That is the flow of the ith component into the system, flow from the system. So what is the concentration of A into the system? That is QCi. Concentration of the A leaving from the system, QCO. And the rate of decomposition of A minus Ra minus R, that is what is your rate of decomposition. That is why it is minus Kc0 into the V. To manipulate the units, R is having the units of moles per meter cube second. So V, that is multiplied so that the units will become moles per second. The units will become the moles per second. And the last term, that is the accumulation term. The change in concentration with respect to the time, that is there. Change in concentration with respect to the time. The outlet concentration that is going to vary. We already talked, whatever the concentration in the tank, the same concentration will go out. So the outlet the tank concentration that is going to vary, that is dCO upon dt. So dCO, that is what the change in concentration with respect to the time, multiplied by the V to manipulate the units. Then next step is at a steady state. So at steady state, the accumulation term that will become 0. The constant Ci is replaced with the CIS. The outlet Q into COS minus K into COS into the V. This is at a steady state. So the requirement of developing the two equation, one equation at unsteady state, another equation at steady state condition. The next is subtracting, manipulating the deviation variables, obtaining the tau term, and taking the inverse Laplace. That is what the step-by-step process for achieving the transfer function for first order system or any system that will be there. We'll see 2-3 systems for the first order system and then we will shift it. So subtracting this one from the another, defining the deviation variables and writing this equation in terms of the deviation variables. Now taking the Laplace transform of that. So after taking the Laplace transform, Q into Ci bar S minus Q into Co bar S minus K Co bar S into the V, which is equal to V into S differential dCO upon dt. That is why S term that is also coming into the picture, Co bar S. You have to remember or recollect the Laplace transform. So taking Laplace transform of the above equation, you will get, and simplifying that means collecting all the output deviation variables and collecting all the input deviation variables. Why we have collected output deviation variables and input deviation variables? That is what our definition of transfer function tells. The Laplace transform of the output deviation variable to the Laplace transform of the input deviation variable. This is nothing but your transfer function Gs. So this is the transfer function. Then manipulating the COS and CIS and writing the adjustments. So manipulation has been done. Then you will get R upon 1 plus tau S. Now this R was not there in the simple system where we have studied the mixing tank. This R appears in the reaction case, and this R or sometimes K is defined as the steady state gain. Is defined as the steady state gain, where tau is the time constant and is represented as V upon Q plus KV. In the case of mixing tank, tau is represented as V upon Q only. In case of a mixing tank, tau is represented as V upon Q. Now in this reaction or CSTR, tau is V upon Q plus KV, where R is your steady state constant, steady state gain. So this is the second transfer function, and in general case R upon 1 plus tau S. The transfer function for the first order systems is R upon 1 plus tau S or 1 upon 1 plus tau S. R is the steady state gain. So is there any steady state gain in the mixing tank? Yes, but its value is 1. R is having the value of 1. That is what the steady state gain. The next example is the mercury thermometer. Now consider a vessel inside which the mercury thermometer bulb that is there. Now this is what? The mercury is inside there. This is the glass wall, and besides that there is a thin film which is available. A liquid film, what we have understood in the heat transfer, a convective liquid film heat transfer coefficient. That is what? The liquid film will be there. And inside that there is mercury. This is shading that is mentioned as the glass. So consider this thermometer placed in a fluid. The temperature Tf of the fluid varies with the time. The aim is to determine the transfer function relating the variation of the thermometer reading T for change in the temperature of the fluid. The expansion or contraction of the glass wall containing the mercury is negligible. These are certain examples, certain assumptions. The liquid film surrounding the bulb is the only resistance. Glass thermal conductivity that is not taken into account, and we are assuming that it is good because its thickness is very small. The mercury assumes the isothermal condition throughout. That means the uniform temperature is maintained inside the mercury. So input minus output, the output, there is no output in this case. The input is only the heat that is going into the system. Heat going into the system, Tf is the surrounding liquid temperature, and the temperature of the mercury is T. So heat is transferred from Cf to T. So HA into the Tf minus T, that is what? Q, the amount of the heat that is going into the bulb. So that is what? The applying unsteady state heat balance for the bulb. HA delta T is Tf minus T, which is output is 0. No heat is going out from the thermometer. You can observe the change in the expansion, but that is not the heat that is going out. So when you take the balance related to the heat, there is no heat which is going out from the thermometer. All the heat which is going into the thermometer, and that is going to achieve the balance between the outer temperature and the inner temperature. That is why we keep a thermometer bulb into our mouth to measure the body temperature. The body provides the heat continuously. The heat is absorbed by the bulb, and as a result you get the change in the level mercury rise. So there is no heat output, but there is a rate of heat accumulation. Accumulation क्या हो रहा है? जितनी भी हीट लिक्विड से ट्रांसफर हो रही है या बॉडी से ट्रांसफर हो रही है, that heat will be completely absorbed, and that will be observed in terms of a change in temperature. क्या चेंज हो रहा है? टेम्परेचर चेंज हो रहा है इस वक्त. So this change in temperature is the dt upon dt. Capital T is the temperature and small t is the time. Capital T is the temperature and small t is the time. So change in temperature with respect to change in time, and to manipulate the units is mCp, Q, which is equal to mc delta T, mc Cp delta T. And to manipulate the units, you require to divide it by the time. So at steady state, this is the unsteady state. One equation is the steady state, unsteady state. Second equation is the steady state equation. Steady state equation में क्या हो जाएगा? Change in the temperature with respect to time is 0. Change in temperature with respect to time is 0 for steady state condition. So this is only the input that is there, and there is no output and no accumulation. So writing the two equations, one is at the unsteady state, second is at the steady state condition, subtracting one from the another, and putting the deviation variables, substituting the deviation variables, and defining the time constant tau, which is mc upon ha, that is defined as the tau, and units having the seconds. So finally, you will get the transfer function as 1 upon 1 plus tau s. In this case, the steady state value, steady state gain, that is not there in this, because the generation or consumption term, that is not there. In case of a reaction, generation or consumption term, that is there. Reactants, they are consumed. So the steady state gain comes in those situations. Now there is a next common, that is the liquid level single tank system. So Q flow rate, which is coming in, and Q0 outlet flow rate, that is going out. And the resistance R, the wall resistance, that is there. Consider a single tank having the cross-sectional area A, a flow resistance wall R that is attached to the pipe at the bottom. So whatever the outlet flow rate that will be there, that will depend on this wall resistance. ये वॉल कितना खोला हुआ है, कितना खुला हुआ है, ये कितना रेजिस्टेंस ऑफर कर रहा है, उसके हिसाब से मेरे को आउटलेट फ्लो रेट मिलेगा. And second thing is that the liquid height, that is going to give me this certain potential. इस liquid height के ऊपर मेरा outlet flow rate रहेगा. The two things are there, liquid height and the wall resistance. H is the liquid height in the tank. Now assume the linear relationship between the flow and the head or the linear resistance. So Qi, that is the inlet flow rate, minus the Qo outlet flow rate, and the accumulation of the fluid is talked in terms of the height. So height, that is going to vary, and that is why dH upon dt term will appear. What is going to vary? What is going to change? Sometimes it is temperature that is going to change, sometimes it's concentration that is going to change, sometimes it is the height that is going to change. So this is Q minus Qo, which is equal to A dH upon the dt. That is what the input flow rate in the meter cube per second, the output flow rate in the meter cube per second, and the rate of accumulation of the liquid into the tank. Then writing it at defining the flow rate and the head relationship. What is the relationship between the flow rate and the head? That is Q0, which is equal to H upon R. The outlet flow rate will depend on the height and the flow resistance. This resistance, this height and this valve resistance. Depending on that, I will get the outlet flow rate. That is what Q, which is equal to the H upon R. Then differentiating this R, dQ0 upon dt, which is equal to dH upon dt. So this dH upon dt is replaced with R dQ0 upon dt, because this is incorporating, basically what we need is the Laplace transform of the output deviation variable to the Laplace transform of the input deviation variable. In this case, the outlet flow rate that is going to vary, as well as the height that is going to vary. So I can have the relationship between the height and the relationship between the outlet flow rate. One by one, we are going to see it. So first is the Q, which is equal to the H upon R. Defining the flow rate and the head relationship, Q is directly proportional to the H and inversely proportional to the R. So substituting this into the basic equation and rearranging it, then at steady state, Qi minus Qos, which is equal to 0. At steady state, change in the inlet flow rate and the outlet flow rate is 0. That is what the accumulation term is 0. Then subtracting 1 minus 2, you get the desired equation. Then defining the deviation variables, capital QI is written here. Sometimes it is QI bar that is written. That is depending on book to book. So time constant, which is equal to tau, which is equal to the AR. So taking the Laplace transform of this equation and rearranging it into the